Chapter 5, Discharge. Name the NFPA standards used for commercial sprinkler systems, 1 and 2 family dwelling sprinkler systems, and sprinkler systems for other residential dwellings up to 4 stories in height. Name the 4 basic types of sprinkler systems. Name the most common type of sprinkler system. Describe how a wet pipe sprinkler system, a dry pipe system, and a pre-action system and a Discharge system works. List the approximate floor area that one sprinkler head is designed to protect. List where a dry pipe sprinkler system is most likely used. List what 2 separate events must occur prior to the initiation of a sprinkler discharge in a pre-action sprinkler system. Describe the main advantage of a pre-action sprinkler system, and explain how an on-off sprinkler system works. Describe where a deluge sprinkler system would most likely be used. List the 4 factors that the water supply system for a sprinkler system should activate, and explain the 3 basic parts of a sprinkler head that are of interest to firefighters. List the 3 basic types of sprinkler heads. List the common size openings for a sprinkler head and the largest size in common use. Identify the 2 things that must be known to determine the discharge from a sprinkler head. Write the sprinkler head formula. Determine the discharge from a sprinkler head. List the major components of a sprinkler head. Explain how to tell if an outside screw and yoke main valve are open. Explain some of the SOPs that are used for operations at a sprinkler occupancy. Explain what conditions most likely exist if a large fire is observed in a sprinkler occupancy when the first fire department units arrive. Describe how a standpipe system works. List the general types of a standpipe system. Discuss the use for a horizontal standpipe system. List the 7 types of standpipe systems. Identify which of the 7 types of standpipe system is used most frequently, and explain how a dry manual standpipe system receives water. List the 3 classes of standpipe systems. Explain the use for each of the 3 classes of standpipe systems, and explain what type of standpipe system is required for high-rise occupancies. Explain how much water at what pressure must be provided at the most remote outlet on a Class 1 standpipe system. Discuss the 1 impairment thing that should be prepared by fire companies for use on high-rise standpipe systems. Explain the recommended standards for the nozzle pressure for solid streams on hand lines held in master stream appliances and for fog nozzles regardless of whether used on hand lines or master stream appliances. Recognize the amount of water that can be expected to be discharged from tips of various sizes. Discuss the development of the discharge formula used in the fire service, and explain the meaning of the coefficient of discharge from a nozzle. Write the discharge formula. Determine the discharge from tips of various sizes. Determine the discharge from an open butt. Estimate the flow from a hydrant outlet. Compare the discharge from 2 different size tips when the nozzle pressure on both tips is the same. Compare the discharge from 2 different tips when they are the same size but the discharge pressures are different. And determine the size of a nozzle tip that has the same discharge capacity as 2 or more nozzle tips combined. Determine the number of nozzle tips of a given size that have the same combined discharge capacity as a single larger tip. The successful extinguishment of a fire with the least amount of loss depends upon delivering the correct amount of water at the correct place at the correct time. One of the objectives of this chapter is to introduce the method for developing the formula for determining discharge from a nozzle tip. A number of illustrations demonstrate the use of the formula on various sizes of nozzle tips. The first portion of this chapter is devoted entirely to sprinkler systems and standpipe systems. The importance of sprinkler systems and standpipe systems to the fire service should not be underestimated. In the latter part of this chapter, a formula is introduced for determining the number of smaller tips required to provide the same discharge as one larger tip. The key to reducing fire losses to a minimum is early detection of fires and the placing of water on a fire as soon as possible after ignition. Those responsible for the protection of a building from fire generally agree that a well-designed, installed, and maintained automatic sprinkler system will overcome many of the deficiencies of risk management, such as building construction and emergency response. Sprinkler systems have been around since the mid-1800s. The first automatic sprinkler system was patented by Philip Pratt in 1872. The sprinkler head was invented in 1874 by Henry S. Parame. In 1881, Frederick Grinnell patented the automatic sprinkler system. The standard for sprinkler systems are contained in FPA 13. Standards for sprinklers in 1- and 2-family dwellings and mobile homes are also contained in NFPA 13D. The NFPA has established that sprinklers typically reduce the chances of dying in a home fire by 1/2 to 2/3. There are 4 basic types of sprinkler systems: a wet pipe system, a dry pipe system, a pre-action system, and a deluge system. Wet pipe systems are the most common and reliable of the 4 types. The wet pipe system is filled with water and it is under pressure at all times. The type of system is used in areas that are not subjected to freezing. Water is held in place within the head by a fusible link or some similar device that is designed to melt or break apart at a predetermined temperature, thereby releasing the water onto the floor. The typical discharge of water from the sprinkler head is approximately 15 gallons per minute. Each sprinkler head will protect approximately 100 square feet of floor space. Here's the picture of a typical wet pipe system. Notice the different components. You have the fire department connection, you have the local alarm, you have the main riser, and then you have the sprinkler heads as well as the test valve. Another system is a dry pipe sprinkler system, and this one is used in areas where freezing is likely to occur. In lieu of water, the system is filled with air under pressure. When a fire occurs and ruptures a sprinkler head, the air escapes, which trips the dry pipe valve, allowing the water to exit the system and put out the fire. NFPA Standard 13 requires that the system be designed so that the water will reach the most remote sprinkler head within 60 seconds. A pre-action system is similar to a dry pipe system. The difference between the two systems is in the manner that the water is allowed to enter the system. With a pre-action system, water is held back from entering the sprinkler system by an electrical operated valve known as the pre-action valve. Here's a typical pre-action system. The pre-action valve identifies a developing fire, which opens the pre-action valve. A sprinkler head operates to permit water to flow onto the floor. A variation of the standard pre-action system is referred to as the on-off system. When the fire is extinguished, a separate thermal device cools, which shuts off the water flow. The deluge system is equipped with open sprinkler heads. The tripping of the fire detection system trips a deluge valve, which immediately releases water to all of the opening heads. The deluge systems are primarily found in specialized industrial situations where a fast-moving fire may make it necessary to quickly extinguish the fire. So here's a great picture of a deluge system. Notice all the sprinkler heads in the warehouse are open. So as soon as the system is activated from the deluge valve, water is supplied to the entire area. This of course is different from the other systems, where each individual sprinkler head must be tripped in order to activate. Residential systems are smaller versions of wet or dry pipe systems, and they are designed to control the size of the fire or extinguish it to allow the occupants to escape. Residential systems generally use a check valve, but they are not required to have a fire department connection. Regardless of the type of sprinkler system installed, the system must have a reliable water source. In most urban areas, the most common source is the public pipe service. In rural areas, water is generally supplied by private tanks, reservoirs, lakes, or rivers. Here's a picture of a couple of different types of pendant sprinkler heads. Notice the different devices that are used to activate. Here we have a glass bulb, and on this one you have a piece of metal that is a fusible link. In both cases, when the temperature reaches the pre-designated temperature, either the bulb will melt or break, or the metal will melt, releasing the water. Regardless of the source of water for a sprinkler system, the source should include the following criteria. The system should be reliable at all times. The system must supply an adequate amount of water for the sprinklers and an adequate pressure. Also, the water supply must be adequate to supply the amount of water anticipated for the duration of the fire. The system must provide for the fire department hose in tandem with the sprinkler systems to operate. The sprinkler heads are the heart of the sprinkler system. The typical head has a half-inch opening. The operating temperatures of sprinkler heads vary from 135 degrees to 575 degrees. The temperature rating of a sprinkler head can be identified by the color coding on the sprinkler frame or by the frangible glass bulb. The amount of water discharged from a sprinkler head depends upon the size of the opening and the pressure to the system. The most common formula available for determining the discharge is as follows. Q is the amount of discharge in GPM, K is the coefficient, and P is the discharge pressure in PSI. So Q equals K times the square root of P. So a half-inch sprinkler will generally have a K factor of about 5.5, and that is a constant. You will be given that. So what would be the discharge from a half-inch sprinkler head that has a K factor of 5.5 and a discharge pressure of 25? So 5.5 times the square root of 25 equals 27.5 gallons per minute. When the sprinkler head has a half-inch diameter, the solution obtained by either formula will provide a good approximation of the discharge. Control valves. All sprinkler systems must be designed so that they can be shut down after the fire has been extinguished. They also need to allow for periodic maintenance of the system or modifications. The control valve is generally an outside screw and yoke known as an OS&Y and is located at a point inside the building where the water enters the building. An OS&Y valve can be identified as being open when all the threads on the valve are shown. When they are not, it can be deemed closed. This is one way to shut off all water to the sprinkler system after a fire. Here is a picture of an outside screw and yoke valve with the rear valve closed. So this means it's closed, and this means it's open. As you can see here, you can see the threads indicating the valve is open. On this one, you can see no threads, so that indicates the valve is closed. If the main shutoff is located outside of a structure, it is generally off what is known as the post indicating type valve. This valve has a small window that will either show whether the system is open or closed. An FDC, with the exception of residential systems, all sprinkler systems should be provided with an FDC. And this is basically a pre-pipe plumbing that goes directly into the sprinkler system. It allows for the fire department to supplement and aid in providing water and pressure to the system. Pipings from these inlets should bypass the main sprinkler shutoff so that water can be supplied to the system in the event that the main valve has been shut off. The main valve being shut off during a fire is the primary reason that a sprinkler system does not extinguish a fire or hold it in check. Here's a good example of an FDC located on the outside of a building. Some departments have a policy that the first or second engine company arriving at a sprinkler occupancy should lay a line into the fire department connection. If smoke is showing on arrival, the pump operator should start flowing water at a pressure of 150 psi to support the system. The reason being it's 150 psi because that is the maximum pressure you can apply to the system to get the most water out, or gallons per minute. Once you start going over 150 psi, the pressure causes a reduction in the amount of volume, or gallons per minute, you get. Fire department officers should take two precautions when operating at fires where sprinkler systems are installed. First, hose lines must not rob the sprinkler system. This is most likely to happen when the officer in charge places hose streams in operation to protect exposures, feeling secure that the fire is being held in check by the sprinkler systems. Second, a sprinkler system should not be shut down until the officer in charge is certain that the fire has been extinguished or is under absolute control. Standpipe systems is an arrangement of pipes, valves, and hose connections that is designed to move water from a source to a hose connection that will be used to extinguish a fire. Standpipe systems may be of the vertical or the horizontal type. The vertical type is used in multi-story buildings, while a horizontal system is used in one-story structures. The supply piping from a vertical system is referred to as a riser. A well-designed and constructed standpipe system is absolutely essential for many high-rise buildings. Primary contributions of horizontal standpipe systems are expediency and convenience in large buildings where the fire may be located a long distance from the building entrance. Types of standpipe systems. There are 7. You have an automatic dry standpipe system, an automatic wet standpipe system, a combination of the two, a manual dry standpipe system, a manual wet standpipe system, a semi-automatic dry standpipe system, and a wet standpipe system. An automatic dry standpipe system, like a dry pipe sprinkler system, has air under pressure in the piping instead of water. With a standpipe system, firefighters have to wait for the air in the system to bleed off prior to water reaching the nozzle. The automatic wet standpipe system is connected to an adequate water supply and is filled with water under pressure at all times. Regardless of the standpipe outlet to which the firefighters connect an attack line, water under pressure is provided to them when the outlet is open. In the semi-automatic standpipe system, water enters the piping of an automatic dry sprinkler system when a sprinkler head is open and the air is released. Once the piping is filled with water, the system is capable of adequately supplying a fire department attack line anywhere in the protected occupancy. A manual dry standpipe system is not connected to any water supply. The only manner for the system to be filled with water is for the fire department to lay a line from the pumper to the FDC and introduce water into the system that way. A manual wet standpipe system is connected to a small water supply. In order to provide water to the system so that it can be used for firefighting, it is necessary for the fire department to lay a line to the FDC and pressurize the system. Standpipes have several classifications: Class 1, 2, and 3. Class 1 systems are to be used primarily by government or private fire personnel who have been trained to handle large hose lines, such as a 2.5-inch line. Class 1 system in high-rise buildings must be of the automatic or semi-automatic type. Class 2 systems are designed primarily for use by trained building occupants. These systems must be capable of supplying 100 gallons per minute of water at 100 psi at the most remote outlet on the system. Class 2 systems can also be used by fire department personnel. However, many times fire department personnel are persuaded from using these because their maintenance and upkeep is unknown and can lead to system failure. The hose that is provided is only an 1.5-inch single jacketed hose. Firefighters should change the hose and connect their own, as they are more reliable. Standpipes are divided into, the 3 different classes. The Class 3 system combines the features of a Class 1 and a Class 2 system. They are equipped with a 2.5-inch outlet for use by fire department personnel and an 1.5-inch outlet with hose attached for use by building occupants. The system must be able to support simultaneously the use of the 2.5 and the 1.5-inch outlet. Discharge formula. Fire streams are intended to discharge a sufficient amount of water to extinguish the fire. Most officers rely on the fail-safe principle. If there is any question about whether a certain size line will extinguish the fire, then the next largest line should be chosen. The fire personnel should be familiar with the 2 primary factors involved in the discharging of water. They should have some idea of how much water can be discharged from various size lines. They should also be familiar with the formulas and methods of estimating the amount of discharge from a hose line. Many fire departments have standard pressures for certain lines and nozzles. For example, 50 psi for a smooth bore hand line, 80 psi for a smooth bore master stream, and 100 psi for fog nozzles of both hand line and master streams. Discharge is obviously the amount of water coming out of an opening. The amount of discharge is simply the area times the velocity. So we know how to figure the area of a circle, 0.7854 times the diameter square. And we know how to figure velocity. When we know the pressure, velocity is 12.14 times the square root of pressure. So when we put these together, this is what we get. Gallons per minute equal 0.7854 times the diameter square. If we multiply them all out together, you come up with the GPM formula, 29.7 times the diameter square times the square root of nozzle pressure. And again, you should refer back to those standard pressures that we mentioned earlier for a solid line, a fog line, and master stream devices. The coefficient of discharge makes estimating the flows the actual gallons per minute instead of a theoretical flow. The discharge from a nozzle tip. We can figure out the discharge from a nozzle tip by inserting the diameter and the pressure into the GPM formula. So, what is the discharge from an 1.5 inch tip at 50 psi? So we take 29.7 times 1.5 squared times the square root of nozzle pressure. It is important to remember that you must do exponents first. So 1.5 times 1.5, then multiply that by 29.7, and then of course get the square root of 50 and multiply again. And that gives you 472 gallons per minute. The open butt discharge formula. An open butt basically refers to a hose line without any nozzle attached to it whatsoever, or to an outlet from a hydrant. Figure 5.24 illustrates the three different design hydrant outlets, each having a different coefficient of discharges. Here's a good example of the different coefficients. The general accepted coefficient for a hydrant is 0.9. If we multiply 0.9 into the GPM formula, the simple formula for open butt is this. Gallons per minute equals 27 times the diameter square times the square root of pressure. So, what would be the discharge from a 2.5 inch hydrant with a discharge pressure of 65 psi? So that would be 27 times, of course, 2.5 times the square root of 65. And that gives us an answer of 1,360 GPM. The next subject is very important for the pump operator to understand. We configure the available water from a hydrant by comparing the static and the residual pressure. Static pressure, again, is the pressure on the hydrant when no water is flowing. Residual pressure is what's remaining after the hydrant is flowing. If we hook up to a hydrant and there is 80 psi static and we open the discharge, what happens to the pressure from the hydrant? Obviously, the pressure drops. The reading on the gauge is what type of pressure? And that is, of course, the residual pressure, because now we are flowing water. That is what's left into the ground. And using that formula, we can figure out how many more gallons per minute we can get out of the hydrant. If the pressure from the hydrant went from 80 psi to 72 psi after the water is flowing, how much of a percentage drop did we have? And that answer is 10%. So that is basically a round number. So you take 80 psi minus 72, and that is going to be 8. And then, of course, you turn that into a percent, and that's basically moving the decimal point over 2 points. And then, of course, we round it up, and that makes it 10%. So let's say we are flowing 250 gallons per minute in the above situation. If the pressure drops 10% after we are flowing, we know we can flow 3 times the amount of water, or 750 gallons more. We get this from this chart here, and this is located on page 189. Many times in fire departments, you'll have a pump chart that already has this listed, so you don't have to recall it from memory. So, if the drop is between 0 and 10%, you can get 3 times more water. If it's between 11 and 50%, you can get 2 times the water. If it's 16 to 25, you can get 1 times the water. And if it's more than 25%, no more water is available. So let's do the same flow. 250 gallons per minute and the static is 80 psi. After we open the discharge and begin flowing water, the pressure drops to 64. How much more water is available from the hydrant? The simple formula for comparing discharge when the nozzle pressures are identical, but the nozzle sizes are different is D divided by lowercase d square, where d is the large tip size and the smaller d is the smaller tip size. So, how much more water can be flowed through a 2-inch tip compared to that of a 1-inch tip when the pressures are the same? You plug in the numbers into the formula and you get 4 times as much. So what this formula is trying to illustrate to you is the larger the tip, the more gallons per minute you will get out of the nozzle. Comparing discharges when tip sizes are identical. The increase in discharge from the same tip as the nozzle pressure increases can be found by comparing the square roots of the nozzle pressure. An increase in discharge equals the square root of the higher pressure divided by that of the lower pressure. So, how much greater is the discharge from a 2-inch tip at 100 psi nozzle pressure than that from a 2-inch tip at a 50 psi? So, increase in discharge equals the higher number over the lower number in square root. So there will be a 1.41 times as much water discharge at 100 psi than at a 50 psi. The formula for determining the size of a single tip that has the same discharge as the combined discharge from 2 or more tips is as follows. Equivalent nozzle diameter will equal the square root of discharge 1 square plus discharge 2 square plus discharge 3 square, and so forth and so on, divided by 8. So, your question, if we have 3 tip sizes, 1, 1.5, and a 1/2 inch, what single size tip is equivalent to the 3 combined? First, transfer the numbers into the eighths and then apply them to the equation. So 8 for the 1 inch, 12 for the 1.5 inch, and 4 for the 1/2 of an inch. So that is the square root of 64 plus 144 plus 16/8, which equal a 1.87 tip. Will flow the same amount as the 3 tips combined. Several tips replacing 1 tip. To determine the number of smaller tips that have a combined discharge capacity of 1 large tip, you use the following formula. N is the number of smaller tips required. D is the diameter of the large tip, again in eighths. The smaller d is the diameter of the smaller tip in eighths. So how many 5/8 inch tip will it take to most nearly equal the discharge capacity of 1 1/4 inch tip? Plug in your variables and you get 10 divided by 5. That becomes 2, and then 2 times 2 is 4. So the answer would be 4. Okay, gang, so we've covered a lot more in this chapter as well. Don't let it blow your little minds. So if you have any questions, please call me at 706-357-0162 in the office, or you can email me at aroberts@athenstech.edu. Or look in Blackboard for the list of my virtual office hours. Until next time we talk, be safe.